let's have a look at the questions on page 58. So what we've got here is we've got our inverse binomial, and knowing that, I'm just going to look through and find the info I need. So they sell boxes of 6 dinner plates, so that is my N, number of trials or sample size is 6. I'm also told that 22.7% of them are returned because they have at least one broken plate. So that is saying the probability that at least one plate is broken is 22.7%. So if I'm thinking in terms of my number line, 0, 1, 2, 3, 4, etc., how many broken plates could be returned? In fact, it could only go up to 6. Then greater than or equal to 1 means 1 or any of the other numbers above it. So it's saying that probability is 22%, 22.7. So we need to work out the probability of 0. That's always our starting point. So what I can do is I can say 1 minus the probability of being more than 1. So 1 minus 0.227 gives us a probability of 0.773. So that's the probability of getting 0, is 0.773. Okay, so there's our first step. Once we have that, this is where we need to remember the formula. So the probability of x is, and this is the full formula from the formula sheet, pi to the power of n times 1 minus pi to the power of n minus x. Now, because we are going to substitute in an x value of 0 into that formula, what that's going to do, hang on, there should be a x. So because I'm substituting in x equals 0, that means this formula is going to simplify. So x equals 0, this first term is going to simplify to 1. Anything to the power of 0 is 1, and I've got 1 minus pi to the power of n, because n minus 0 is n. And instead of the pi, I'm actually just going to write that as p, because I personally prefer to do p, then when students don't get it mixed up with pi, the number of 3.14156, all that stuff. So that's where I'm at now, and what I'm going to do is I am going to substitute into that formula. So my probability of 0, I found that before. Here's my probability of 0, so that is 0.773. 1 times 1 is 1, so I'm going to get 1 minus p, and n, the number of plates in a box that we were told that n is 6. So I put the 6 in place of the n. Now I'm going to jump to my calculator, and I'm going to come down to the equation mode, and I want to use F3, which is solver. And now I'm going to type in that equation that I have just written down. Okay, so this equation here, the only thing I need to remember is that the calculator doesn't have a p. I'm going to use x because the calculator has this x variable that it uses instead. Okay, just a generic one. So I'm going to type in 0.773. Oh, I'm typing on my screen rather than over here. 0.773. And then to do the equals is down here above the decimal point. So shift full stop gives me my equals. And then I'm going to say bracket 1 minus, and now I'm going to use that capital letter X, close bracket. This little almost triangle, that is my power, it's called a caret, so to the power of 6. And I'm going to say press execute, just so that it enters the equation basically. Now I get this option here coming up, which is my solver. So I'm going to say F6, go off and solve it. And so that tells me that my answer and instead of calling it x, I'm going to go back to calling it p, because that's what I'm trying to find. P is 0.0420 to 4 decimal places. So that is the probability for a single plate being broken. So the chance that one plate is broken is 4.2%. And that means we now have, it meets the requirement of 22% being in a whole box. Okay, part B. Department manager wants to see the proportion of returned boxes reduced to 13%. So people return it when they have a broken plate. So the chance of at least one broken plate is they want that reduced to 13%. And we are asked to find the percentage of broken plates required to achieve that. So we need to find that little value of p. They say find the little value of p. So we are going to do our probability of 0. So if the probability of being more than 1 is 13%, then the opposite is 0.87. So now I'm going to use my simplified formula. Probability x of 0 equals 1 minus p to the power of n. And I'm going to substitute in. So 0.87 equals 1 minus p, which is what I want to find. And our n is 6. I've got 6 plates in a box still. So I'm going to go back to my solve it mode, and I'm going to just jump back out, and I'm going to say delete all of those formulas so that I can clear it out and start again. And now I'm going to type that in. 0.87 equals 1 minus capital X to the power of 6, and go off and solve it, and that gives us the p there. So that says the probability, in order to get to more than 13% returned boxes, the chance of a plate being broken needs to be down at 0.229 or 2.3%. So that's the maximum percentage that is required in order to get the proportion of boxes down to 13%. Okay, so part C. Another way is to reduce the number of plates in each box. So when we talk about the number of plates, that's talking about our n. So it says use the answer from part A, and so when we did part A, we got the answer there of 0.042, so we're going to use that. So I'm going to use p of 0.042, and we need to now find the maximum number that could be in there to get a return rate, maximum return rate of 13%. So return rate, remember they're returning it if there's at least one broken plate in a box. So we're told that we want that return rate of at least one to be less than or equal to 13%, which means the opposite of having no breaking plates in a box. We want that percentage to be at least 87%. Okay, so we use our formula. Probability x equals 0 is 1 minus p to the power of n, and we're going to put this in as 87%, and 1 minus the p value that we've got there, the chance of a single plate being broken, is 0.042, and that's to the power of n. So I'm going to remember that I'm going to enter in my calculator that as the x variable, and I'm going to jump across and clear that. So I go to my delete and F1, yes, delete that. So now I can type in 0.87 equals bracket 1 minus 0.042 to the power of x. And I'm going to say go off and solve that, and it now gives me an answer here. So that's my n. So that n is 3.25. Now comes the next extra bit that I need to do when I'm finding n, is I'm finding a number of trials or the sample size, and I can't have 0.25 of a plate. Well, I can, but I can't sell a 0.25 of a plate. So we need to round this either to n equals 3 or n equals 4. And we need to work out which of those will give us this required probability of 13% return rate maximum. So what I'm going to do is I'm going to say, right, I know my P is 0.042, so that's a single plate. If the sample size n is 3, then what would the probability be of getting no broken plates? And I'm going to look at that number and see, is that greater than or equal to 87%? And then I'll try that with n equals 4, and I'm going to see which of those gives me the answer that I'm looking for. So I'm going to go back out to my menu, go into my stats menu, and distributions, binomial, and be PD. So I'm going to put in x of 0. I'm going to start with the number of trials of 3, with a probability for a single plate of 0.042, and that gives me there a probability of a box of not broken plates. If there are 3 in there, that would have an 87.9% chance of containing no broken plates. Then I'm going to just try the same thing, so I'm going to go and do number of trials is 4, and that gives me an answer there of 84%. 8423. So what I'm going to do is I'm going to look at that criteria. I want my chance of no broken plates to be at least 87%. This is the one that's going to give me no broken plates of at least 87%, so I can say therefore n is equal to 3. Okay, the last part of that question is it now asks us to calculate the expected return rate. So I found out how many plates I'm going to put in a box. I'm going to put 3 in a box, and now I need to know what the return rate will be. So our return rate is when at least 1 is returned. So we want to know what's the probability that at least 1 plate is returned, and that's 1 minus the probability of no plates. So I want to do 1 minus that 0.8792, and that gives me 0.1208. So they've got a 12% chance. That's their return rate, is a 12% return rate. Okay, let's go on and have a look at question 2. So Nick grows courgettes and he puts 20 plants in a row. Some don't thrive, and he's found that all 20 plants thrive at an average of 39% of the rows, and we want the probability for a plant, a single plant. So that's saying we want to find that little p. Here we've got number of plants in a row is 20, and the probability that 20 plants thrive, so all 20 plants, that probability is 0.39. So I'm going to go back to the whole formula now, because we don't have the probability of 0, which is often what we need. So my full formula is this one here. We go p to the power of x times 1 minus p to the power of n minus x. Okay, so what I know is when I now substitute in the value x of 20, this first term here, this n choose x, that is going to still simplify to a value of 1. Equally, when I look at this part, so n is 20 minus x is 20, so this term here, 20 minus 20 in the power, that becomes power of 0, and anything to the power of 0 is 1. So I'm going to get 1 times px times 1 equals the probability that x is equal to 20. So the formula still simplifies in a very similar way as we talked about earlier. Okay, so now using that, I know my probability of all 20 plants thriving, that's 0.39. And p to the power of x is 20. So there is my equation. So I'm going to jump across and go back to my equation menu and do solver, and I'm just going to clear the one that was there, and now I'm going to put that equation in. 0.39 equals x to the power of 20, and solve that, and that gives me p 0.9540. So that would be the probability, and the question asked, calculate the probability that a plant thrives. There's a 95% chance that a single plant will thrive, and there's a 39% chance that all 20 plants will thrive. So notice that we're looking for that difference between a single plant and a group of plants. Okay, question 3. Tossing a fair coin. So when we've got a fair coin, we know the probability of getting a head or a tail is 0.5. And we're being asked how many times, so we've been asked to find n, the number of times, and they want to be at least 95% certain of getting at least one. Oh, and that should say head. Sorry, bad typing skills. So that tells me the probability of getting at least one head, we want that to be at least 95%. Okay, so I need to do the reverse, work out the probability of 0, and we want the probability of 0 to be less than 5%. So I can do the simplified version of the formula. Probability x equals 0 equals 1 minus p. Sorry, that's not terrible. 1 minus p to the power of n, and in this case our probability of 0 is 5%, so 0.05 equals 1 minus probability, which is of a single head, which is 0.5, to the power of n. So I'm going to clear my formula, go back, delete, yes, and I'm going to put in 0.05 equals 1 minus 0.5 to the power of x, and solve that, and that gives me n equals 4.3. So now I need to think, okay, n, can n be 4.3? Well, it can't be 0.3 because I can't throw it 0.3 of a time. So I need to now decide, is this going to be rounded down to 4, or am I going to round that up to 5? Which of those would be correct? So to check that, I'm going to find the probability of 0 for both of them. And we know the probability of a single head is 0.5. So I want to find, if I toss it 4 times, what's the chance of not getting a head? And if I toss it 5 times, what's the chance of getting no heads? So back to our stats menu and binomial, and I'm going to do number of trials is, start with 4, and the probability of head is 0.5. And so that will give me a probability of getting no heads if I toss it 4 times would be 0.0625. If, however, I had a sample size of 5, then that would give me a probability of no heads of 0.03125. So that there I need to now decide from those options which of them gives me the probability of no heads being less than 5%, and that is this one when n is equal to 5. So we can say therefore n equals 5. Now that I've got that, I'm just going to go back to the question. The final part of the question says if they toss it that times, so in this case 5 times, what is the probability that she'll get at least one head? Okay, so the probability of getting at least one head is 1 minus the probability of not getting any heads, which I've already just gone to find. And so 1 minus 0.03125 gives me a probability of 0.96815. So there's a 96% chance of getting at least one head if they toss it 5 times. Okay, question number 4. A mechanic has a number of jelly beans and they come in 10 different colours, and it tells us they are in equal numbers. So what that means is that the probability of getting any colour is 1 out of 10. So he wants to know the minimum, he would like a minimum of 1 jelly bean. Okay, minimum of 1 means at least 1, to be put in 2/3 and at least 2/3 of the packet. So he wants the probability of getting at least 1 jelly bean to be at least 2/3. And we want to know how many jelly beans. So that's saying find the value of n. So that's our next step. So I'm going to start with that probability of greater than 1. I need to change that to the probability of 0 being less than 1/3. Then I can use my simplified formula. So 1 minus p to the power of n, and in this case the probability of 0, we want that to be 1/3, and 1 minus the probability of a single jelly bean is 1 over 10 to the power of n. So I'm going to go into my equation mode and solver, and I'll just clear that. So I've got 1/3 equals 1 minus 1 over 10 to the power of x, and I'm going to say solve that for me, and that tells me n is equal to 10.43, and so I need to decide, am I going to round that down to 10 or am I going to round that up to 11? So that's when I'm going to check what's the probability of getting 0 for both of those scenarios and which one meets the criteria of being less than 1/3. So in my stats menu, distributions binomial BPD, and I'm going to set my number of trials first of all to 10, and the probability of a single one getting a jelly bean is 1 out of 10, and so that would give me a probability of not getting any jelly beans in the packet of that are read of 0.3487. And if I test the number of trials with 11, then that gives me a probability of no red jelly beans of 0.3138. So which one of those gives us a probability of being less than 1/3? And it has to be this one down here, so n is equal to 11. So I can say therefore n equals 11. So if I now look at that last part of the question, I want to find what percentage of packets will have at least one red jelly bean. So I want the probability of getting at least one red jelly bean, and so that's 1 minus the probability of getting no red jelly beans, which is this 1 minus 0.3138, which will give me a probability of 0.6862. Gosh, my brain just went blank. Awesome. So there we go. And so that is the chance that the packet will have at least one red jelly bean. So there's a difference, remember, between the probability of the individual jelly bean, which is little p, and this probability of the whole packet of jelly beans. Awesome. Thanks, guys.